This is part 2 for the ELEKIT TU8100. If you missed part 1, be sure to watch that before this one so you'll see how I went through troubleshooting to find the component and the full explanation on how the circuit works. I got the part for it. Let's put the part in and get this unit working, shall we? Let's do it. Now to recap, I'm not going to show the whole video, but I'm going to show you the output from the PIC that I came to determine was defective in part 1. And we actually even swapped the MOSFET from the filament to the output just to verify that the MOSFET wasn't bad. So there's pin 15. We have about 4.5 volts peak to peak there. And now we'll look at pin number 16. As you can see, pin 16 is about 2 volts on there. So there's the difference between pin 15 and pin 16. Now remember, I've already changed the MOSFETs. I put in the one that was the switching MOSFET for the filament in place, just to verify, to rule out a bad MOSFET. The chip is bad, for sure. Now it's going to go into shutdown. This is a very well engineered system with the microcontroller that monitors all the voltage. So what it's doing is it's monitoring for over voltage, under voltage, over current. It's also monitoring the cathode current to the vacuum tubes themselves. And anything that falls out of spec is going to shut the system down. In this case, one MOSFET's not being driven on because we have a missing or incorrect voltage to drive the gate of the MOSFET. So, got the new part. Let's get the new part in and see if it fixes it. Okay, we got the PIC in for the TU8100, so let's change it. This is one of these times I wish I had a desoldering station, because this is a plated through board and it's difficult to remove this IC. I spent a lot of time prepping this with solder wick. I got the chip out, no problem. It was a little bit of a chore, to say the least, to get all that solder out so I could get that old chip out and get the new one installed. Okay, got the old PIC removed. How we know that we're completely clear is you can shine a light from below and you can see through all the pins. Therefore we know that we're clear. Except for a bit of rosin that's in there, but all the solder is clear, all the pins are out. Now we can go ahead and mount the new one. Incidentally, the reason it's connected is I did do it, fired it up here just to make sure everything was still in the same state that it was before I got into it. And that black wire you see, that's just a secondary ground. I wanted to make sure that we weren't having a problem just due to a bad grounding, because when the top board is out, it's not grounded to that stud. Although there is a ground that passes through the multi-connector. So that black wire you see was kind of unnecessary, but I put it on there just for testing. So this is a bit of a challenge to get this in, but once we get this through the board, we'll get it soldered in place and see whether the unit is actually going to do anything and produce any sound. Okay, we got the new IC in place. Let's take a look at pin 15 and pin 16 on the scope. Now remember that pin 16 before had no drive signal, so let's take a look at pin 15 and 16. Power is on. We'll just wait for the unit to actually turn on the high voltage. Okay, there's pin 16 and there's pin 15. As you can see, our signal is the same for both pin 15, pin 16. We have our drive signal back. Woohoo! We think this is all great, right? No, I've created another problem. So what I found is when I was taking a look at it, as I say, we got our drive signals back here going into our gates of our FETs. But I was looking at the voltage measurements. Pin 10 and pin 11, these are the current consumption monitor loops for the FETs. If your FET is drawing too much current or too little current, it will be reported on the IC, and the IC will go into a shutdown state. Just like it will if the voltage is too high or the voltage is too low. Monitored on pin number 3 here, which is the B plus monitor coming in through here, right? And you've also got your current for the tubes in pin 1 and pin 2, so that if the tubes were to go into an avalanche condition, you'd be shut down. Also, if the FETs are drawing too much or too little current, it will also shut down. So I was measuring 0.117 volts on pin number 10 here, but pin number 11 was measuring 0. So I go back and I look at the voltage on the source for the FET, and I find that this one here is at 0. Now this is the FET, remember, that I took out from the heater when I was testing the amplifier before. I swapped this one and this one around to verify that the FET was good. And I think probably what happened is when I removed this one from the position on the top board, I damaged it and put it on this one. Now I had no drive before, so I had no drive signal, so nothing was showing up. Now I got a drive signal, but there's no current. So I pull the FET back out and swap them back around, and of course I've got no filament control. So bridge the source and the drain together to give me filaments for testing. And let's see what happens. We have sound. Everything is working now. Pin number 11 is your monitor voltage for source off of FET1. So as the FETs are switching back and forth, the current is being monitored by the PIC. So what I had to do is I had to jumper the source and the drain to keep the filaments lit. So the filaments come on as soon as the power is turned on now, as opposed to being delayed, because this MOSFET is screwed. This is the original MOSFET from here. I swapped those before when I had the bad drive IC, and I had no drive, if you remember, and I'll show you the waveforms from it, but I had no drive at all. I put the new IC in, and bloody thing was still shutting down, but I had drive. I checked the MOSFET again, and the MOSFET is not turning on, but now it is. Now if we look at our voltages, my light. If we look at the voltages now, to say our plates, our voltages will be fine now. If we look at pin number 6, for example, 190 volts, which is good. It was coming a bit low before. Pin 7, 4 volts, that looks okay on our cathode. Pin number 9 is the plate to the triode side, 96 volts, that's about right. because it's being fed through a 220k resistor. Our B plus down here at D2, 212 volts. This was coming up a little low before, if you remember. The reason it was coming up a bit low is because one MOSFET wasn't operating. We look at the waveform again with the scope. We'll see that our waveform is nice and clean and both sides are firing. So let's take a look at the MOSFETs. So here we go, FET1. That's the, what's that one? That's the drain. Yeah, drain of FET1 and FET2. Okay, nice square wave for both. And our drive signal from pin 15 and pin 16. I got to adjust my scope here for this, but there's our drive signal from pin 15, and there's our drive signal from pin 16. Therefore, fault on this unit was the PIC. Why that MOSFET went, I don't know. It may have been damaged when I swapped them around before. I don't think so, because I didn't. It's not like I put excessive heat or anything on them. I don't know why that one failed, because that one definitely was working when it was here originally for the filament. It was turning the filament off and on, and when I had no drive signal, that's when I swapped it over to here, right? So the one that's in here now, this is the original one. Both of these are the original two that were from the inverter. This is actually the one that was originally in for the filament. I swapped it, it went bad. Don't know why, but it did. Anyway, kind of threw me a bit of a loop there, but once I saw my drive signal, I was measuring my voltages. I was seeing some voltages that were a little bit off from what I was getting off my own amplifier. And this one here, when I got to pin 10 and pin 11, this is the big one here that told me that the fault was actually current. There was no drive signal, or the MOSFET was being driven on, but it wasn't passing any current. So there you go. Interesting problem. Now I have to find a MOSFET. The one that's in here is not really critical. It's the only thing it's there for is to do this. So when the amp is first turned on, it's to put a delay on the tubes, because normally when you turn on something on, you get a bit of an inrush because the heater is cold. So when you first turn it on, you get well, if I let it cool right down, it'll do it. But you'll get if I let the tubes cool right down, when you first turn it on, you get a bit of an inrush, and the filaments will kind of flash a little bit brighter and dark, right? It's from the inrush surge. That's what this one here is for. This one is to delay the operation, to delay the power going to the filaments on the tube until the power supply and everything stabilizes, and then it turns them on. Like 5 seconds later, it turns on the filaments to allow the filaments to start heating up. Not a critical one. We'll probably change it out anyway just for the hell of it, but it's not critical. It's to say the amp will work fine as it sits. If I let this thing cool down and turn it on, you'll see the filaments will go brighter initially and then dim down to where they're supposed to be. Now, of course, why that happens is all incandescent bulbs, vacuum tubes, incandescent light bulbs, whatever, when the tungsten filament is cold, the resistance is lower. So what typically happens, and this is why all incandescent light bulbs will blow when you first turn them on when they age, right? Incandescent light bulbs rated at 1,000 hours. If you turn the thing on and leave it run constantly, it'll last a lot longer than turning it on and off, because every time you turn on, when the filament is dead cold, every time you turn it on, the resistance is lower. There's going to be an inrush. Because the resistance is lower, it's going to draw more current, and it's going to heat it up real quick. And that initial inrush is what makes the filaments pop in incandescent bulbs. Anybody who's experienced the old AA5 vacuum tube radios, the All-American 5 with the 5 tubes in series, you'll always notice it's always the rectifier tube. When you first put the power to them, it lights up really bright and then it dims down. And that's what these will do if I let them cool down to the point where they're at room temperature. When I first turn this on, you will see the filament in here will initially go really quite bright and then dim down, because what's happening is the internal resistance is lower and it's getting the full 12 volts put across the heater until it heats up. So the idea behind this is to bring it up slowly. So it lets the power supply stabilize, and then it turns them on slowly just to stop that inrush. Okay, this is what will happen if the tubes are cold. You see? The inrush. You saw that one right up there. That's what the delay MOSFET is for. It's just to stop the inrush to the tubes when you first fire it up, when they're cold. And it's just due to the internal resistance of the filament when the tubes are dead cold. And that's the only reason that exists. So this MOSFET is just a standard N-channel MOSFET. It's not doing any type of heavy current, heavy lifting. It's just switching on and off 12 volts DC to the tubes. So any N-channel MOSFET is going to work. I have one here, a little bit bigger. It'll do the job just fine. So let's get this other one out of here. These tubes are red hot. Let them cool for a bit. I've had it running now for a couple of hours. We're going to swap this one out. Let's get these things cool down a bit. We'll swap this MOSFET out, and then I can get this thing back together. To lift this one out, all I got to do is just heat up the heat sink part of it here. It's soldered down to the board, using the board as a heat sink. So we'll just heat it up a bit and just lift it off the board. And then I'll just heat the pins from below and remove it. Okay, this one here should be the same basing as the original. Put the shield back on here while I'm at it. So I'm just remounting the shield. This is just a piece of circuit board that is used to shield any noise that may come from the high frequency switching transformer. It's at 125 kilohertz, so you're not going to ever hear it, but we'll put the shield back in place, get the board mounted again. Should probably test this before I make it too permanent. Okay, our filaments are on now with the delay, which is what we want. And we'll have our sound momentarily. There we go. Now he's going to put the just going to turn it off here for a minute. I'm going to get the board in place, and then we can put the screws in. So the board's in place there. I'm just going to mount the board properly. Then I can put this unit back together and run it on its test run in its case. Okay, the unit is now reattached in place, ready to go back together. Next step will just be to put it into the box, and then I'm going to run this thing for multiple days before sending it back. There it is working. Okay, just mounted in the cabinet now, so I'll remove the tubes for this one last time. I'm thinking that MOSFET that was bad, that was originally the filament MOSFET that I pulled and put into the power supply when I was initially testing it, because I had no drive from the drive IC. And I think probably what happened is when it got pulled out of the board, it got damaged, because as you notice, when I pulled it back out, one of the legs broke off, and that's the one that there was no signal to, right? The source. That was the source. Anyway, that's the one I put into the power supply when I was troubleshooting the bad IC. So we had no drive. And when I put the new IC in, we had our drive signal back, but this thing wasn't conducting. Put it back in over here, only to find out that it wasn't working for the filament. So I have a feeling that MOSFET got damaged when I pulled it the first time when I was testing the IC. That's why it failed. Make no mistake, the fault with this amp was the IC. Get all the screws back in. I actually picked up the part today to fix this from the importer for all of North America. And he was telling me about some of the exciting amps that they've got, that I'm chomping at the bit to build another one. A little more expensive one. So I keep you guys in the loop if I decide to go down that road and drop several $1,000s on a new amp. I will be building it on my channel, but I'd love to build the 300B that uses the 300B triodes. I'd love to build one of those ones. So that's the 80, I think that's the TU8600. That or the 8700. 8700 is a single-ended pentode amp that apparently can use like 15 different tubes. I'll have to look that one up and see. But I'd like to build the push-pull. There's a 30, I think it's 35 watts push-pull amp. I would like to build that one. And I'd like to build a 300B amp. Because one cannot have too many vacuum tube amplifiers. And anybody who's ever heard the sound from a tube amp will know what I'm talking about. That's it. Thanks for watching. We'll catch you in the next one real soon.